finding the average value of a finite set of numbers is easy. You just have to add up what those numbers are, and then you divide by the number of numbers that there are. So for this set here, I will write it in sigma notation. You'd say the sum of a sub k, from k equals 1 to, I have 5 of them, and then you would just divide that by 5. When you add these all up, you get 24 and divide by 5, and 24/5 is the average, taking into account the positive and negative numbers and also 0. Add them up and divide, that's what it is. It gets a little more complicated when you have to average, or when you're required to average an infinite number of numbers. For example, this set here, if you have a function, if I ask, how can you find the average of all of these y values along this curve? Well, it's kind of different from the finite sense in that you have a continuity of all these values. What could the average be? Well, if I ask students to approximate it, how would you go about maybe finding an approximation for it? What you might do is, you might want to say, you partition your region, and what you would do is pick a value of x to represent the contribution of that part for the function, and you would add those up and divide by however many there are. For example, if we have 1, 2, 3, 4, 5, 6, 7, 8, you would pick, say, 8 values of x, do f of those numbers to get these 8 y values, add those up, and divide by 8, and that would be the approximate average. But again, that's only a representation of the continuum of values that are actually there. To get the average of a continuous set, we need to use an integral, but the process is exactly the same. What we're going to do is partition this region into a certain number of rectangles. Let's say that we're going to use n subdivisions. So, and this will be delta x1 and delta x2, etc. And the last one will be delta xn. We'll say that they're all of equal size. We're going to want them of equal size because we want each section to have an equal representation among the average. So what we're going to do is choose a value of x inside each subinterval. There's an x1 star in there, and there's an x2 star in the second one, and so on and so on. And we're going to add all those up and divide by the number of them that there are. Using sigma notation, it would be the sum of f of x k star from k equals 1 to n, right? The sum of all of the outputs, and you would divide that by the number of subintervals that you chose to use. Now this is almost looking like it's a Riemann sum. We can turn it into a Riemann sum and thereby take the integral. By getting rid of this somehow, what you find is if all of your delta x's are equal in size, then n times delta x, however long that is equal to the length of the interval, right? Because there's n of them, they're all the same length. When you multiply them, you get b minus a. So this 1 over n can be replaced with, if you cross multiply here, bring the n down, bring this down, you'll get delta x, or b minus a, equals 1 over n. So performing that replacement, when you put that in there, you'll see that this gives you delta x, b minus a, times the sum of f of x k star, k equals 1 to n. And so you can bring this in to the other side. So it'll be 1, delta x. And now you have your Riemann sum, of which you can take the limit. The limit of this, as n goes to infinity, gives you the definite integral, 1 over b minus a, because that's on the outside, and this turns into the integral from a to b of f of x dx. And that is the average value formula for f of x on an interval a b. Show you what that means. If you have a function here, rewrite this equals f average. It's just some number. It's the average value, but it has a geometric interpretation too. if you take the b minus a and you multiply both sides of this equation by b minus a, you get the integral of f of x, dx from a to b, equals the average value, f at times b minus a. What's the geometric interpretation of this? This is just a rectangle whose length is the length of the interval and whose height is the average value. And it says this equals the integral of the actual area. So what the average value is, the geometric interpretation is, it's the area of the rectangle, it's the size of the height of the rectangle that will exactly contain the area underneath the curve.